In this segment, we are going to look at an algorithm used in constructing multiplier circuits, which is called the shift and add multiplication algorithm. So, what is this algorithm used for, first of all? We have seen adders and subtractors as part of combinational circuits, and we have another category of combinational circuits which are called multipliers. The simplest possible implementation of a multiplier is an array multiplier, which is something I have described at length in a separate video. Now, the shift and add multiplier is another implementation of the multiplier, which uses a slightly modified algorithm which makes it computationally easier for the system. So, why so? We will look at that first, and then we'll try to understand what is this algorithm and how it works. So, if you look at the structure of an array multiplier, which is used for multiplying two-digit numbers, this is what it looks like. When both your multiplicand and multiplier are two-digit numbers, you see that it requires 4 AND gates as well as 2 adders. So you need these. The adders again are they have an elaborate circuit in and of themselves, which you might be aware of if you have studied combinational circuits before. So we can see that just to multiply two numbers which are 2 digits each, you need such an elaborate setup. So if your numbers are going to be larger, you have a 3-digit number or a 4-digit number, the number of adders you require are going to increase because the number of partial products will increase. So to include that amount of hardware in a single circuit becomes expensive because logic gates are expensive naturally. So we want to create a multiplier circuit which is a little less expensive on the hardware perspective if possible, which is why we came up with this idea of a shift and add multiplier. So what is the need for another multiplier? Why is the array multiplier not good enough? Because it works based on partial products and adding them up. As the number of digits increases, for example, if you look at this 4-digit cross 4-digit multiplication, you have quite a large number of partial products, and then because an adder can only add 2 or 3 quantities at once, the number of adders it will take to add up all these partial products is going to be very high. And adders in themselves are complicated circuit elements which have a lot of circuitry, a lot of gates involved, XOR gates, AND gates, and so on. So in order to reduce the hardware complexity, we want a simpler algorithm. Simpler probably not in terms of computation, as in when you try to multiply two numbers normally and then when you try multiplying them using the shift and add method, you might find the normal method easier. But in terms of hardware, in terms of the number of gates that go into the circuit, the shift and add circuit is a little less complicated as compared to your array multiplier circuit. So we will first take a quick look at the normal multiplication. We are going to do binary multiplication of two 4-digit numbers, 1101, which is 13, and 1110, which is 14. So the first number is usually called the multiplicand, the second number the multiplier, and this is the normal binary multiplication, and this is your result. So how does binary multiplication work? Because every digit is either a 0 or a 1. Of course, you start multiplying each digit of the multiplier with the multiplicand. If the digit of the multiplier is a 0, the partial product is just going to be all zeros. If it is a 1, it is going to be the multiplicand itself. So here it's our multiplier has a 0, so you will just get 0, 0, 0, 0. Here it is a 1, so your partial product is going to be the multiplicand itself, 1, 1, 0, 1. The only catch being at each step you shift one bit left as you include the partial products. So at the tens place it is you leave this one gap, and the third time you leave these 2 steps, 2 bits left shift, and so on. So this is how normal multiplication works, right? Binary or even your decimal multiplication. So we are going to look at something called the shift and add multiplier, where instead of shifting the partial products to the left, we will be shifting the multiplier 1 bit right. So when I will be explaining the algorithm formally now, but to give you a very high level overview of why it is called shift and add, That is what it is. Instead of shifting this one step left each time, we shift the multiplier one step right. And why that helps, we will see. So we are going to look at the algorithm now. We will first see what are the quantities we need to initialize. M is our multiplicand. In this case, it is going to be 1101. C is the initial carry, which is 0. As we proceed with the multiplication, we might come up with some carry value. N is the number of bits in the multiplicand or multiplier, which is 4 in this case. B is the multiplier, the second number, in this case 1110. A is something called the accumulator, which is where we will be storing our partial products, and A will give us part of the final result also. And the initial value for A will be 0000. And how many bits do I have in A? Equal to n, number of bits in M. So because M is a 4-digit number here, because both M and B are 4-digit values here, we said A equals 4 zeros. If let's say M had been a 5-digit quantity, then A would be 00000 and so on. So what have we seen so far? Shift and add multiplication is an algorithm used to construct multiplier circuits, which are on the hardware perspective simpler compared to your array multiplier. What are the initializations we make? M, the multiplicand, B, the multiplier, N is the number of bits or number of digits in these numbers in the multiplicand and multiplier, C, the initial carry is a 0, and A, accumulator, is also set to 0. The size of A will be as many bits as N, that is the number of bits in M or B. So with that initial knowledge, let's get started with the algorithm. So here is the flow chart which depicts the algorithm. Let's walk through the flow chart once, and then we will perform the multiplication for the example we saw on the previous page according to this algorithm, so that we get a clearer picture. Start. Check the LSB of B. LSB stands for least significant bit, which is the rightmost digit in the number, the units place digit. And B we know is the multiplier. So check the rightmost digit of the multiplier. Is it equal to 1? So this is what we did, right? In normal multiplication, if the multiplier digit is 0, your partial product is going to be all zeros. If it is a 1, your partial product is going to be the multiplicand itself. We saw this. So that is what we are checking here. Is the last digit equal to a 1? If it is equal to a 1, you add the multiplicand to the accumulator. Accumulator is a variable which we initialize to 0, and it will be storing the intermediate partial product values and part of the final result also. So if it is a 1, the partial product is going to be the multiplicand itself, right? So A plus equal to multiplicand. So you add the multiplicand to the accumulator, and then you right shift CAB. If it is not as 1, that is if it is a 0, directly you are going to right shift CAB. So what are these? What is the CAB stand for? The three values: C carry, A accumulator, and B the multiplier. You right shift each of them by one digit. So let us say, for example, we had these values: C, A, B. C is going to be initially 0. A is also 0000. Let us say, for example, this is B, or let's have a non-zero value for A also. Let us say, for example, let's consider this is our CAB at some step. When I say right shift CAB, it means that every digit in this sequence moves one position to the right. So this 0 comes here, 1110, 110, this 1 is lost, and the blank space in the left is always filled with a 0. That is what we mean by right shift CAB. Let's try doing another right shift. So this 0 comes here, 0111, 011. The last digit of the sequence will always be lost, and to the left you will always add a 0 when you do a right shift. So this is what right shift means. Okay. So what did we do? We checked the least significant bit of your multiplier. If it is a 1, you add the multiplicand to your accumulator and then right shift CAB. If not, you directly right shift CAB. So this is what I meant when I said instead of moving the partial products to the left, we are shifting the multiplier to the right. So after this is done, you reduce the number of digits by 1, as in you reduce n by 1, because one of the multiplications has been done. So when your multiplier has 4 digits, you will do 4 sets of multiplications, right? So the first of them has been completed. So decrement n by 1. Now check if n is equal to 0. If not, go back here and repeat the same process. Now your b has shifted to the right by 1 step, right? So the least significant bit is a different digit now. So initially it was 1101, then it became 0110. So this was the LSB. Now this is the LSB. So again you check the LSB, again you repeat the same process until n becomes 0. Once n is 0, your answer, you stop at that point, you don't do any more shifting or multiplication, and your answer is just AB put together. As in, let's say my n becomes 0 at this point, then my final result would be this 00111011 or 111011. This would be my final result. It's important to note that AB is not the product of A and B, it is just A, B put next to each other. So we will look at a formal example now, but this is the algorithm. Now with that algorithm in our mind and with this example, which is what we started out with, let's try solving it. So initially my n equals 4. Hope this is visible. N equals 4. We have C, A, B, C is 0. A is initially 0, 0, 0, 0. And my B is a 1110. First step, check the least significant bit of B. It's a 0. If it is a 1, we have some addition to do, but here because it's a 0, no addition, just shift right CAB. So it becomes 0, 0, 0, 0, 0, 111. We add a 0 here, and we decrement n by 1. So n becomes equal to 3. So now again we have CAB, just copy the values 0, 0, 0, 0, 0, 0, 111. Check the least significant bit of B. It is a 1. So accumulator plus equal to M. This was what we were supposed to do. What is our M? 1101. So your accumulator becomes, C remains the same as of now. Accumulator becomes 1101. B is 0111. Next step, after the addition, go back, right shift CAB. Now let's do the right shift, shall we? 0, 1, 1, 0, 1, 0, 11 and a 0 here. And then we decrement n becomes 2. So now what are the values I have? C, A, B, 0, 0, 1, 1, 0, 1, 0, 1, 1. Again check the least significant bit. It is a 1. So accumulator plus equal to M. What is M? 1101. So accumulator will become this plus 1101, which is 1, 1, 0, 0. The carry goes here, it becomes a 1. So this is 1, 0, 0, 1, 1, 1, 0, 1, 1. Now shift right CAB. What does it become? 0. This 1 comes here. 0, 0, 1, 1, 1, 0, 1. So this is my C, A and B at this point, and now my n equals 1. So this is where we had paused. Again check the last least significant bit. It's a 1. So accumulator plus equal to M. Our M is 1101. So we add that 1101. It becomes a 0, 1, 1, 0, 1. So it is 1, 0, 1, 1, 0, 1, 1, 0, 1. Now shift right. So this becomes 1, 0, 1, 1, 0, 1, 1, 0 and a 0 here. Now n becomes 0. So what does the algorithm ask us to do when n equals 0? Stop. The answer is just AB. So let's see what the answer is. So my answer would be 1011 0110. Let's check if this matches the answer we obtained by normal multiplication. 1011 0110. So that is shift and add multiplication for you. Here's the first page, and here is the second, and this is the algorithm.